some things are related, others are not. Suppose you randomly select a person from a crowd who is significantly taller than the average. In that case, there is a good chance that they will also weigh more than the average. Statistically, one quantity also contains some information about the other. Quantum physics allows for even stronger links between different quantities. Different particles or parts of an extensive quantum system can share a certain amount of information. There are curious theoretical predictions about this. Surprisingly, the measure of this mutual information does not depend on the size of the system, but only on its surface. This surprising result has been confirmed experimentally at the TU Wien, Vienna University of Technology, and published in the journal Nature Physics. Theoretical input to the experiment and its interpretation came from Max Planck Institute for Quantum Optics in Garching, FU Berlin, ETH Zurich, and New York University. The researcher says, let's imagine a gas container in which small particles fly around and behave in a very classical way like small spheres. If the system is in equilibrium, then particles in different areas of the container know nothing about each other. One can consider them completely independent of each other. Therefore, one can say that the mutual information these two particles share is zero. In the quantum world, however, things are different. If particles behave quantumly, then it may happen that you can no longer consider them independently of each other. They are mathematically connected. You can't meaningfully describe one particle without saying something about the other. For such cases, there has long been a prediction about the mutual information shared between different subsystems of a many-body quantum system. In such quantum gas, the shared mutual information is larger than zero, and it does not depend on the size of the subsystems, but only on the outer bounding surface of the subsystem. This prediction seems intuitively strange. In the classical world, it is different. For example, the information contained in a book depends on its volume, not merely on the area of the book's cover. In the quantum world, however, information is often closely linked to surface area. The research has now confirmed for the first time that the mutual information in a many-body quantum system scales with the surface area rather than with the volume. For this purpose, they studied a cloud of ultra-cooled atoms. The particles were cooled to just above absolute zero temperature and held in place by an atom chip. At extremely low temperatures, the quantum properties of the particles become increasingly important. The information spreads out more and more in the system, and the connection between the individual parts of the overall system becomes more and more significant. In this case, the system can be described with a quantum field theory. As long as the system's temperature does not reach absolute zero, which is impossible, this shared information has a limited range. In quantum physics, this is related to the coherence length. It indicates the distance to which particles quantumly behave similar and thereby know from each other. This also explains why shared information doesn't matter in a classical gas. Quantum information plays an essential role in many technical applications of quantum physics today. Thus, the experiment results are relevant to various research areas, from solid-state physics to the quantum physical study of gravity.